Hey, and welcome back. My name is MrCaproni, and I'm an AP Statistics teacher at Western Hills University High School. And you're joining us today for video 19. Now, we've been talking a whole bunch about hypothesis testing. In fact, we've spent the last 2 full videos on it. So this is going to be day 3 of hypothesis testing. In particular, we are looking at the one proportion z-test. Now, if you feel like you're getting lost or behind, or you'd like to see future videos that you might not have time to see on TV, feel free to look at YouTube and you can search MrCaproni with no space, no period, and you will see all of my videos there that cover everything from video 1 all the way up to this video, and it'll include all the videos after this. So again, if you want to catch up, see what's going on, you can always check out those videos there. Now, last time, we went ahead and checked out hypothesis testing day 2 by looking specifically at what a p-value was and identifying specific tests that we can use and the type of test that we would use when doing a hypothesis test. Today, we're going to review a bit of that p-value and actually look at an example of it, and then we'll spend the rest of the time actually doing some examples so that we can see exactly how this whole thing looks beginning to end, so that we can see how it goes into the calculator, and so that we can learn how we would write a conclusion for some hypothesis test like this. This is going to be the major day, so I hope you're going to learn something new, and please join me now as we start day 19 of AP Stats. We're going to start off by looking at the hypothesis testing process like we have the last 2 days. And there are 7 steps that we're going to do an entire hypothesis test from beginning to end. The first one is to check your conditions. You actually can't do this until after you do step 4, where you decide which test it is that we're going to use. But I always list it as step 1 because it is the most frequently forgotten step in the process. And a lot of times students will get points off on the AP test because they forgot to check the conditions that went along with their choice of test. So don't forget to do that, and we'll do that in our example today as well. Step 2 is to write your null and alternative hypothesis. Remember, this whole hypothesis testing is all focused around the null hypothesis and the alternative hypothesis. The null, also known as the HO or the HO, is when the given information. It's what we assume to be true at the beginning. But what we're going to do is try to prove that an alternative to that is actually true. And we'll do that by going out and taking a sample, and then we'll find the probability of that sample occurring if the null hypothesis were true. Now, once we have our null and alternative written out, we can go ahead and write out any other information they gave us in the question. That's when we decide on which test to use. At this point, we've really only done one proportion z-test, but we'll do much more in the future. After we get that chosen, we pick which of the types, either our left tail or right tail, or our two-tail test, and then we'll plug everything into our calculator, which we'll see for the first time today. Then we'll go ahead and compare the p-value with the level of significance so that we can write our final conclusion. Now, I don't want us to forget exactly what our p-value is. This is not the probability that our null hypothesis is true. That's usually given to us in the question. We're not finding that. The p-value is when we go out and we take a sample and we try to find the probability that that sample would have occurred knowing what the true proportion was in the null hypothesis. So we assume the null hypothesis to be true, we go out, collect a sample, and then we find out hey, what's the probability that that sample should have happened? Now, if that probability, or p-value, comes back extremely small, then we have enough evidence to say that the original null hypothesis is probably false. Because in that case, it means that we got something that was so rare that we believed it should never happen, and it happened the first time we went out and took a sample. So in that case, we're able to reject the HO, or the null hypothesis, and we can move on in accepting our alternative hypothesis. Now, if that p-value turns out being much larger, then that just means that the probability of getting the sample that we got is actually pretty likely. So it doesn't change anything. It just means that, hey, the null hypothesis, we really don't have any evidence to reject that that's true. Now, it does not prove that the null hypothesis was true. It just shows that we don't really have any evidence to believe otherwise. It's very important to make sure you understand what the p-value is, because it is the driving statistical force to the hypothesis test. Let's go ahead and look at an example of how we actually find the p-value in a question like this by hand before we would move forward with actually just plugging it into the calculator and having it shoot it out for us. So this example says a large city's DMV claimed that 80% of candidates passed driving tests, but a survey of 90 randomly selected local teens who had taken the test found only 68 who passed. What's the p-value for the one proportion z-test? Now, we're going to ignore all the other steps of the hypothesis testing. For right now, I just want to focus on how do you find the p-value. And remember, this is actually something we already knew how to do in previous chapters because we're just finding the probability that this sample of 90 would occur if the 80% were truly true. All right, so let's take a look here. Remember, the first thing we probably want to take a look at is what is that 68 out of 90 as a percent? Now, sometimes it's nice for our calculator to have it like that because then it gave us the x value, the number of successes. But in this case, for sake of our conversation, let's talk about what it is when we actually divide it out and get it as a percent. So if you do 68 divided by 90, that's actually going to give you 75.5 repeated, which we can just round to, I don't know, 75.6 or something around there. So let's go ahead with that in mind. We're looking at this question saying, what's the probability that our sample would only be 75.6% passage rate if it actually were supposed to be 80%? What's the p-value, the probability that that sample would occur? So instead of going through and writing all of this out by hand, I do have a slide here with all of the work done for us so that we can kind of just talk our way through it. So first off, you see down here this 68 divided by 90 that I had mentioned, that's our probability of success for the sample. So that's what we got as our sample. So we're saying, hey, what's the probability we would get that 75.6% if the 80% were true? Now, how do we go about doing this? Remember, we would first off need our standard deviation. In order to find our standard deviation, we take the probability of success for the assumed correct 80%, times the probability of failure, which would be 20%, divided by your sample size, which is 90, and then take the square root of the whole thing. That gives us about 0.042. Now, from here, there are two ways we could do this. Either A, you could go into your calculator and go to normal CDF, and you would go from negative 9999 up to 0.756, plug that in for the normal CDF, and it's going to ask for the mean and standard deviation. For the mean, you would put 0.80 because that's the assumed mean. And for the standard deviation, we would put in that 0.042. If you do that, your calculator will shoot out this 0.146, which we'll talk about as the answer in a second. The second way to do it would be to go ahead and find the z-score by doing our p-hat, which is our sample proportion, the 0.5 or 756, minus our true proportion, which in this case was assumed to be 0.80, divided by that standard deviation we found in the step above, which was 0.042. That gives you a z-score of negative 1.05. Now, why would you want to find a z-score? Well, instead of using the normal CDF in the calculator, you could also use the z-charts that were usually found in the back of our textbook, or you could find that in the charts that they will provide you for the AP test. So you could either do it using the normal CDF method or use it doing the z-scores and using the charts. Either way, you will find out the probability of a sample like this or lower occurring would be 14.6%. Now, is that high or low? Is that so low that we would be able to reject the 80%? Well, that's what we're going to kind of spend the rest of this video talking about. But in this case, we don't have a clear-cut idea of that answer just yet. So if we were just looking for p-value, this would be how your calculator finds the p-value. But again, great news, we actually won't have to do this work very often because our calculator will do all of these steps for us once we plug in all the information we have. All right, so let's go ahead and go back and answer that question. How small does p-value have to be in order for us to reject the null hypothesis? Now, when it comes down to it, there is no statistical formula for this. You're going to find out it's kind of just something that we predetermine. So when the question first pops up, we'll end up setting a cutoff mark. We'll say, hey, if p-value is lower than this, then we're going to go ahead and reject. If the p-value is larger than this, then we'll fail to reject. All right. Now, we need to make this firm decision at the beginning, not afterwards, so that our whole process is legit. All right. So remember, if your p-value is smaller than our cutoff value that we'll set, then we'll say that we reject the null hypothesis. If the p-value is higher than our cutoff, then we'll say that we fail to reject the null hypothesis. Now, how do we define the p-value to be rare enough for it to be considered a rare event? Well, there's some definitions and some terminology that we need to deal with first. It says if our p-value falls below a given point, we'll reject the null hypothesis, which we said, and we call such a result statistically significant. It means that, hey, this was so low that we think it's a significant event, so we call it statistically significant. And the threshold that we actually set, like the little cutoff number, we'll call that an alpha level. And it's actually going to have a whole bunch of different names that we'll go by, as you'll see in a second. But the alpha level is represented by the Greek letter lowercase alpha. So there's your alpha. That's always the case. Now, this can be referred to as your significance level. It can be called your level of significance, but it will always have this same symbol. Now, sometimes when you see it in print, it's a little bit wider like this, but regardless, it is always called an alpha. That's a lowercase alpha, and it is always the symbol that we use to represent this cutoff idea. If you call that your alpha level, your level of significance, or the significant level, any of those things, those are all represented by alpha. And again, that is the cutoff for where we will say if p-value is lower than that, we reject the hoe. If the p-value is higher than that, we fail to reject the hoe. Now, just like with confidence intervals, we kind of had a set amount. For confidence intervals, we said the common ones were always 99, 95, or 90%. For our alpha levels, we'll actually do the same as that, but on the flip side. So that means that we'll set our levels at either 10%, 5%, or 1%. So in other words, if our p-value is less than 5%, then we're going to end up rejecting our hoe. Otherwise, we'll fail to reject, okay? Now, what can we say if the p-value does not fall below alpha? Well, I just mentioned one way of doing it, but it says that you could, long-winded, say the data have failed to provide sufficient evidence to reject the null hypothesis. But remember, the key here is one thing. We never, ever, ever, maybe I should do red, ever accept the hoe. You never accept the hoe. So we always either fail to reject it or we say there's not enough evidence to reject it, whatever. We fail to reject, we never accept the hoe. Now, I know what you're thinking, Mr. Caproni. I don't understand what you're saying until we actually just do one of these. Well, now's your time to shine, because here we go, jump into our first example. Now remember, we're going to do a full hypothesis test all the way through, the whole thing, every bit, all 7 steps. So remember, what are the 7 steps? 1, we need to check our conditions. 2, we need to make sure to write our null and alternative hypothesis. 3, we need to write out all the information that the question gives us. 4, we need to decide which test to use and which type of the test to use. Number 5, we're going to plug everything we got in the calculator, this will be the first time you'll see that. Step 6, we need to compare our p-value to our alpha level or level of significance. And step 7, we have to write up our final conclusion. So first things first, let's go ahead and read through our question. It says, anyone who plays or watches sports has heard of the home field advantage. Tournaments in many sports are designed to try to neutralize the advantage of the home team or player. Most people believe that the teams tend to win more often when they play at home. But do they? Is this actually a thing? If there were no home field advantage, the home teams would win about half of the games played. So you would expect them to win 50%, lose 50%. To test this, we're going to use the games in the Major League Baseball 2012 season. That year, there are a total of 2,430 games when you look across all the different teams. It turns out that the home team of each of those games won 1,295 of those games out of the 2,430, or 53.29% of the time. Could this deviation from 50% be explained just from the natural sampling variability, Or is it evidence to suggest that there really is a home field advantage, at least in professional baseball? Now, remember, we're not actually going to check these conditions until we pick a test, but we're going to go ahead and just pick the test right now because we know the only one we've covered so far is our one proportion z-test. Now, how would I know that this is a one proportion z-test if we had other tests in our tool belt right now? Well, the fact that it gives us a 50% to use as our norm and then gives us one sample that had a 53.29%, this is obviously a proportion where they gave us one number and then they gave us a sample number as well, and both of them are proportions. So it should be pretty obvious that this is a one proportion z-test. Now, the question from there comes into, would we be doing a left tail test, a right tail test, or the two-sided test? And in this case, we want to know if you have an advantage by being the home team. So in other words, in this case, we're actually going to be looking at a right-tailed test because when we look through here, we don't care if they win less games. We want to know if there's an advantage. So we only care about more games. And we're going to use that more when we write our HO and HA in just a second. But as of the moment, we can knock out step 4, which was deciding which test to use. And we're going to say that this is a one proportion z test. Now, once we're in to knowing which test we're dealing with, then we can start looking at our conditions. Now, before we do this, let's break a little bit of this question down on top of what we just said. Notice here it says 53.29% of them won when they were the home team. Now, 53% is really close to 50%. But the question is, this is also a huge sample size. So is that 3%, the 3.29% difference, going to be a large enough difference for us to claim that it is a thing to have home field advantage? I don't know. That's what we're going to find out. So again, we chose to use one proportion z-test. Now we need to go ahead and check our conditions. Number one, is this random? Now, it doesn't mention anywhere in the actual question if this is random or not. So we're not really sure, but here's the deal is it used all the games from one season. So this wasn't just one team, it wasn't just one like type of person or anything like that. It was all the teams in a set season. Now, could seasons be different from this season to that? Yes. So we're not exactly perfect on a random condition. But because every team was included and there was no bias towards what type of team, we're going to say that this is pretty much good to go. All right. Now, the 10% rule. This was only one season of games, and there's been a lot of seasons of baseball, which means there is no way one season would be 10% of all the games that have ever been played. So we are safe to say that this sample is less than 10% of the whole population. Also, even though this is just for baseball, they're actually using this to project home field advantage for all sports. Now, you could argue, well, this doesn't really work for all sports because it's only baseball. And that would be a valid argument. But either way, there are far more than 24,000 regular baseball games. So we're still going to be under that 10%. Now, in terms of the success fail condition, this is actually going to be really easy to hit. Because our numbers are so high, when you multiply them by your probability of success, which is going to be 0.50 for success and 0.50 for failure as well, it's going to pretty easily be above 10 because our numbers in there are just so huge. All right. So remember, our sample size is 2,430. 2,430 times 0.50 gives you 1,215. Now, we actually know in this case that it's 50% both sides because 50% win, 50% loss. So we are going to be able to say both of them are going to be 1,215, which that number is very easily bigger than 10, which means we will be able to fulfill all three conditions. So we have now checked our conditions and decided what test to use, which means our next step is to dive in and write out our null and our alternative hypotheses. First things first, let's write out that ho and the ha. All right. Now remember, our null hypothesis, the ho, is just the original information that we would expect to be true before we took any type of sample. So in this case, it said pretty clearly that we would assume that if there were no home field advantage, then it would be the same percentage of wins versus loss regardless of if they're home or away. So that means that we're using 50% as kind of our set null hypothesis beginning. So that means because we're dealing with proportions, we'll put a P on this side. It is always an equal sign for the HO. And then in this case, we're dealing with 50% as the proportion for our null, like our assumed value to be true. Now, in this case, we keep most of those pieces the same for the HA, and that will actually be for all hypothesis tests. We always kind of keep the left and right the same. Now, the middle part is the thing that changes, and in this case, it will either be less than, greater than, or not equal to. We want to know if there's a home field advantage, meaning that we want to know if that percent should actually be larger than 50%. So that means that we want this proportion to be larger than the 50%. And that's going to be our alternative hypothesis. That's what we're going to be able to claim is true if we are capable of rejecting our null. Now, after we go ahead and write down our ho and our ha, then we should make sure we still have all the other bits of information we may need. So for example, they do give us X, our number of successes, which was 1,295. And then they also give us N, our total number in the sample, which was 2,430. And they give us P hat, which is the proportion of success. That's actually kind of just bonus that they gave us, that was the 53.29%. Because in reality, we could have found that ourselves by just doing the 1,095 divided by the 2,430. So these three things were all given to us as well. In this case, the question does not define an alpha. So our level of significance is not given to us. Now, just like with confidence intervals, usually as a default, if they don't give you one to go with, you want to go with the 0.05. So in other words, when we are all said and done here and we have a p-value, if our p-value is less than 5%, we will reject the ho and accept the ha. If the p-value is bigger than 5%, then we will fail to reject the ho. And if you can't reject the ho, you're done. You don't get to move on to the ha. You can't accept anything else in life. If you fail to reject that ho, it's over. You're done. All right. So let's go ahead and see, how do we plug something like this into the calculator? Now you're going to notice again that we are using the TI-Nspire. TI-Nspire is what I use for my class. If you use a different calculator, I'm sure you can just Google, for example, if you're using a TI-84 or TI-83, just Google hypothesis test TI-84, TI-83, and you'll be able to find right away how to do it on your calculator that you're using at home. But for my class on the TI-Nspire, we go ahead and go into the calculator just like normal. So remember to do that, you just click there. Mine's going to look a little bit different because I'm using an updated version of the software. As you can see, it's a CX2. So from there, we go into the menu, go into your menu. And just like with confidence intervals, we're able to go into statistics. Now, before we were going through either probability to distributions, or we were going in through statistics into distributions, and then confidence intervals. But now we are moving on to stats test. So this is a hypothesis test. So stats test is what we're going to do. And I've told you guys that there's going to be a whole bunch of these as we go along. As you can see here, here's a list of all the ones that we'll be covering in this class. Now this year, the AP test is a little special that it's actually going to drop off 7 through A down here, but we will still be responsible for covering 1 through 6. Now, we have said it over and over again. The test we've been talking about is the one proportion z-test. So this is what we're going to click on. Now, in here, it's only going to ask us for 4 things. It asks for the PO, the number of successes, X, and N, our sample size, and then it wants to know what our alternative hypothesis was. Now notice that PO right here is also down here. What is that number? It is the proportion that you use in your null hypothesis. So in our case, we used 0.50 as our null hypothesis number, okay? Then from there, our x was our number of successes. Well, what was our number of successes? We said that it was 1,295. So we go ahead and put that in, 1,295. Then we go down to our sample size. What was our sample size? Our sample size was 2,430. So we want 2,430. And in terms of our alternative hypothesis, again, we went through the trouble of writing this out. So we would have it, we have P is greater than 50%. So in this case, we want to use the one that has greater than, which is the top option. Now, I have put in all the data our calculator needs in order to do a hypothesis test. Now, once I hit OK, it will go ahead and give me this little printout here. Now, it gives us a lot of important things here. Number one, it gives you the Z-score. So this is how many standard deviations from the mean it would be if we were to go through the steps of finding our Z-score. Next, it gives you the p-val. In this case, it's 0.000586. That's an extremely low p-val. And that's kind of going to be a big one that we're going to have here in a second. That's what's going to make our decision for our hypothesis test. Now notice it also has the p-hat. As I told you guys, you don't have to find that, and the question kind of gave it to us as a bonus. And it writes out the n, which is just the sample size that we plugged in. So again, what's the big number we want to pull from here? We want to pull this guy right here, which is our p-value of the 0.000586. So I brought over a lot of that information from the calculator and I put it down here, and I wrote, just as a reminder, when do we reject the HO and when do we fail to reject? Well, if P is less than alpha, we reject. If P is greater than alpha, we fail to reject. So looking at what our calculator printed out, we have a p-value of 0.000586. Now, that would be the equivalent of saying this, because we don't have our zeros added on, so I can put them here. This is actually essentially saying we're comparing 500, all right? So alpha is way bigger. So in this case, our p-value is less than alpha, all right? Because our p-value is 0.000586 and our alpha was 0.05. So it is way, way less. And in fact, if we had chosen at the beginning an alpha of 1%, which is usually the lowest people go, it still would have been well under it, which means in this case, we are going to get to choose to reject that HO. Now, remember, once you reject the HO, your next step is that you are allowed to accept that the alternative is true. So even though in our original question, 53% was the home field advantage sample, and that seems really close to 50 in the grand scheme of things. But in reality, it turns out that that is indeed far enough for us to reject the 50% and accept that it's actually higher than 50%, meaning that the home field advantage is really a thing in baseball. Now, if we were to write a final sentence for this question, a full conclusion, we would want to use the fact that we rejected the HO, and we would want to restate the alternative hypothesis in context of our question. So if you wanted to say something, I don't like writing this out because it can be different for anyone, but you kind of need to include some set things in it. So how would I say it? In this case, I would say, after running a one proportion z-test, we have enough evidence to reject our null hypothesis and accept that the probability of winning a game at home is actually greater than 50%, meaning that home field advantage is a real thing. Now, that seems long-winded, but after you do all the work for a hypothesis test, why waste getting the wrong answer because you didn't take the time to write it out? So you could shorten that up in a lot of different ways, but that's how I would give it. I would say, obviously, the fact that I rejected the null hypothesis, and I would want to make sure to state what my alternative hypothesis is in context of the question. Now, at this point, we have gone through the entire 7-step process. It actually doesn't take very long when you think about it, because we pick the test, which a lot of times you can figure out within a second or two. Then we have to write our HO and our HA, all right? We already checked the conditions in the beginning, so that was checked off. We wrote down our additional stuff, which only took a few seconds as well. Our calculator did all the hard work and gave us the p-value. We just had to look at the p-value and the alpha and see which one was bigger. Then you make your conclusion statement based off of that. This is a full hypothesis test, and this is what we're going to do over and over and over for the rest of the year.
Well, there you have it, guys. That was from beginning to end going through a hypothesis test. It's taken 3 episodes for us to kind of explain this whole process all the way through. But at the end of the day, you can see in the example, this really actually doesn't take very long to do. There's just a lot of pieces that we have to learn how to do. So, we've gone through all of that. I really hope you learned a lot of information from this video. And if I were you, I'd practice this a lot more than what you just saw on here. We've only done one example together, but if you're truly going to take the AP test, you might want to see if your teacher can provide you with more examples of running a 1 proportion z-test, or maybe you want to refer to your textbook so that you can see some other examples that the textbook goes through, or maybe the textbook will give you some example exercises for you to do at the end that you can try looking through there. At the end of the day, though, I would never just look at one of these, and for my class, I'm going to go ahead and post a few more to our Schoology page. So, again, I would practice with this, but there is going to be a whole bunch more practice for us in these videos, because although we may not be looking at 1 proportion z-test anymore, we still have quite a few other hypothesis tests to look through. So, in the upcoming videos, we're going to go through what a 2 proportion hypothesis test looks like, and then we'll start looking to when we have a one sample mean or 2 sample mean. So don't worry, we're not done yet. We still have quite a bit more to go. But I want to thank you for joining me today, and remember, if you're ever getting lost or confused, feel free to check out all of my videos on YouTube at MrCaproni. So just search MrCaproni on YouTube and you should be able to find all of the videos I've made for this AP Stats course. Again, guys, thanks for joining me. Hope you learned something new. And as always, stay fit, stay healthy, and have a wonderful day.